inspection method. Also known as rule of inspection. Rule of inspection was seen in the yesterday's interaction. Very simple interaction was seen, and how to form the dimension and how to find elements of individual row and column of a Y-bus was just witnessed by a simple example. And another example was just to tell you that the information of elemental data need not be given always in admittance form. It may be given in impedance form. You need to transform that impedance form to admittance form. Then you need to take rule how each bus is accessed, how each elements are evaluated and placed in the matrix form. That was what seen in the previous class. Now one addition to that. Suppose the transmission element, let me put you in this way. Suppose I have in this way and I have another bus in this way. If I call this as bus I, if I call this as bus J, like 1, 2, 3, 4 of the system or a problem like yesterday what we have seen, let us imagine there is a transmission line represented like this. And you have, let me draw it for the perfect way of representation, and I would like to interact with you how you account these things. Because these minor understandings will help you great to work for your requirement. Suppose let me write this as Y1, Y1 to let me write Yij, Yi0, Yj0. Hope you are able to understand this representation. This is exactly like this. Suppose if I have ith bus and I have a jth bus, if I represent this data Yij, this is the data. How this line is modeled, I am trying to witness you. The transmission element connected between bus I and J is represented as pi model. Pi model. This is also known as pi model. It can be T model. If it is a very short line, we write it as lumped model. If it is a very long transmission line, it is modeled as distributed parametric model. So I am trying to revisit your understanding. Short line, medium line, and long line. Approximately 80 kilometers, what we call as short transmission line. From 80 to 160 kilometers, we categorize them as medium transmission line, and 160 kilometer and above, we call them as long transmission line. This is one way of classifying based on the distance or the length of the transmission line. Now, why I took this? I took this simply because when I want to represent a transmission line element connected between bus I and J, arbitrarily say Yij is the admittance of that, I just represented the elemental data of that as Yij. It means I have represented it as lumped value. Entire length of the transmission line is considered as the admittance, lumped and placed for the computation. We call this as lumped model. Absolutely, in my mind, it is a short line. Then the transmission line need not be like this way all the time. If the transmission line is modeled as a long transmission line or a medium transmission line, appropriate mathematical representation is necessary. The mathematical representation justifies your quality of work, because this Y-bus, once it is framed, kept in the computer of an energy control center, used for several calculations, load flow study, short circuit study, stability analysis, or any other contingent issues related to power system operation and control, definitely this particular matrix serves as basic requirement. If this is not appropriate, the analysis what we perform for the need or for a particular situation would definitely go deviated or wrong. The decisions taken on which definitely deviate and deteriorate system may suffer. In that regard, proper modeling of electrical components is very necessary. I am trying to emphasize modeling of transmission line, modeling of transformer, modeling of a generator, modeling of a load, modeling of any compensating devices, if so on the system, need to be represented to the truthfulness of that. It's a proper mathematical preliminary. So I am trying to emphasize the need of mathematical representation. For us, let us say very simple. If a transmission line is represented like a Yij, an elemental admittance of a line between bus I and bus J as Yij, this is to say lumped model. Suppose if the line is medium line of by category 160 km to higher, 80 km to 160 km range, then modeling may go by pi or P section like. If it is a pi model, a particular transmission elemental data Yij between bus I and J set to be in pi model, it would look like this. Like I have a bus I have a bus J like your Ij, and this data which is said as a lumped element, it won't be lumped element, it is going to have the representation like this. The elemental admittance between bus I and J and half line charging admittances. I am using the word half line charging admittances of the line connected from bus to the ground and to bus to the ground. This is becoming a pi representation. You may ask me, what may be the another representation of which? The another representation of which is T structure, wherein entire admittance of the line between I and J is cut into two halves like this. Let me explain here itself like this, and we will be having bus I, bus J. This is Yij by 2, Yij by 2. This is half line charging admittance. Let me write Yc by 2. It means this is called a T structure. The entire admittance which I am writing, the elemental representation of an element between I and J is cut into two halves, Yij by 2, Yij by 2, and central to which we represent capacitive representation, admittance. The half line charging admittance is totally represented at the midpoint of the transmission line representation. This structure we call it T structure. And another one which I have represented over here is pi model. So pi and T model are used to represent the transmission line for the length 60 km to 80 to 160 km, like a medium classification. Suppose if you find a problem wherein you have a representation like this, how to account is my understanding over here. Yesterday we had a simple problem, a problem like this. Let me draw it here. A problem which we have seen yesterday, a very simple problem. If a change is required in that, if a change pertaining to a model is there, how to account it? I would like to tell. Like this, we had a sample situation. Let me draw it. Like this, we had a problem yesterday. Hope I remember this. This is like this only. Yes. This one like bus number 1 I wrote, bus number 2 I wrote, 4 and bus number 3 I wrote. Here I had elemental representation. Let me write here for the easiness. This represents me the elemental admittance like this. If I want, I can write this is Y1 2, Y2 3, Y2 4, Y3 4, Y1 3. So this is clear now. Now you tell me whether this is a representation of the elemental data in a lumped manner or in a other like pi r t. It's very clear. It is a lumped model. There is no element between bus 1 and ground or bus 2 and ground. Other way, a element between 1 and 3, y13 is positioned simply y13. It is not having any elemental representation from bus 1 to ground or 3 to ground. Hence, this is short line modeling. Components are represented on the basis of short transmission line basis. Suppose if I visualize this as medium transmission line, how I would view it? I would view each element between bus 1 and 2, bus 2 and 4, 4 and 3, 1 and 3, 2 and 3, an elemental in this way. Let us take this case, 1, 2, y12. If I view this, only this section as a medium transmission line, how I would represent it? If I have taken it as a pi model, let us say this as I equal to 2. I mean, sorry, 1. J equal to, hope this is clear. Then Yij become Y12. This Yi0 becomes Y10. This becomes 20. So I am matching this with this line is represented as pi model. Then how this is going to affect your Y bus calculation? The first question is it going to affect or not? Definitely it is going to affect your calculation. The values which you accounted on the diagonal y11, y22, y33, 44 are surely going to get compelled. What about the off diagonal? Surely not. Because when I have 1, I have a 2. So look at this. At bus number 1, how many lines I have? 1 to 2, 1 to 3. Imagine like y12, y13 is also modeled. Like this I have 1, let me draw here, not an issue. This is bus number 3, by chance, I am drawing vertical. Now I have a line between 1 and 3, let me represent it, nothing wrong in that. Correct? This is y13. Then this line I have to model like this. Then I will have a line like this. A ground here. This is y30. This is y10 like this. This is bus number 3. Can you imagine? Y13 is now treated as pi model. Pi means a horizontal Y13, 1 to ground, 3 to ground. Like this, I can have any number of lines which are there in the system. If at all they are under the model medium transmission section, their representation shall go like either phi or P like. If it is represented in the problem, you are sure to take account of that. You shall not ignore. If you ignore, the elemental accuracy will be lost. Therefore, if it is so, now look into this issue. I will concentrate only bus number 1. At bus number 1, I have 1 to 2, 1 to 3, and this 1 to 2 have elemental data from bus 1 to ground, which I wrote here. Okay. Now what I will do? 1 to 3 also I have an element ground. Now I have y10, y10 like this. I will be in confusion. What I will do? y10, comma 1, 2. What it represents? Admittance between 1 and ground due to 1 to 2 connection. I am able to discriminate. If I write this y10, let me read here. y10, comma 1, 3. What is this meaning? Admittance between 1 and ground because of 1 to 3 connection. So y13, 10, 13, 10, 12. I am able to understand at this point. This way, I need to be very careful about the workout. So if I complete this, I will be able to move next. So I will take up at bus 1 to look into this. Y11, if I want to write, let me write here. Therefore, Y11 refers to 1 to 2, there is a line, let me write here, Y12, lowercase y12. Then 1 to 3, there is a line, Y13. So this was the work yesterday we have done. Now, you at bus number 1. At bus 1, how many elements you are having? 1 is 1 to 2, straight to 2. 1 to 3, straight to 3. And no doubt there is another element from 1 to ground, Y10, 12. This also need to be taken care. Y10 due to 1 to 2. And not only this, there is another line from bus 1 to ground, 10, 13 because of 1 to 3 connection. So this is also an Y10, 13. Now look at this. How many elements you got interconnected to bus number 1? Totally 4 elements. One is Y1 to 2, Y1 to 3, Y1012 representation, Y1013 due to this. So when I represent the problem by pi model, I am sure that diagonal element of your Y bus gets affected. This is true if you add a line or delete a line. Your modification to the Y bus shall go in the computer. You have to devise a program or write an algorithm that keeps tracking. This may be due to a fault. Imagine a new line is connected between 1 and 3, or there occur a fault. Line is broken. If line is broken, means isolated. This structure needs to be deleted from the calculation. So you must have an algorithm or a computer program which is able to understand and get your need for that. Therefore, the mathematical representation works very necessarily. Therefore, when I have this Y12, Y13, 1012, 1013 as your decimal element. You look, these two are new elements for you. Yesterday they were not there. When I had only short representation, these two were invisible. When I have pi model, then these two appeared. Then I must take care. You may ask me, when all I should take this? Unless it is given in the problem, you should not take. Or you have to take only when it is represented as pi model. If it is not given, no need to take. Now look into this. So Y11, you got it. Now coming to bus 1 only, what is Y12? What is Y12? Capital Y12? There is no change. This is negative of the Y12. It remains as usual in the earlier discussion. This term or this term will not come in picture. That is not going to come in the picture. Therefore, you must be careful at bus 1. Only the diagonal gets affected by half-line charging admittances at connected bus. Only diagonal like 1, 1, 2, 2, 2, 3, 3, like this get affected. Y12 will not. What about Y13? This is minus Y13. If it is Y14 by chance, this is minus Y14. If it is there, otherwise 0. Of course, there is no connection. 1 to 4, there is no connection. This is 0. But I have to write it. Because I have to admit it in general. There can be an element between bus 1 and bus 4 also. So I have to admit that for my requirement. Okay? Similarly, this representation, if I take it to bus number 2, you please tell me, at bus 2, how many lines you find? 2 to 1, you have a line. 2 to 4, you have a line. 2 to 3, you have a line. Hope you are able to capture me. There are 3 transmission lines. One is already represented over here. Yet 2 to 4, 2 to 3, you have to establish. Let us do it and work it out. So, when I work with the Y11, this is the only change you notice, rest remains same. So, you are sure that diagonals get modified. Hope this is clear. I just take it out. I will just extend my work with bus number 2. At bus number 2, I have 2 to 4. Let me draw here. I just make another bus location somewhere wider here. I make it bus number 4. We do it closer, nothing wrong in that. Bus number 4. So I shall do this way. Bus 4, I have a line like this, Y24, and from here I just write half line charging admission. From here I will write half line charging admission. This is Y2024. This is Y40. You may write 24 or 4. That is it. Let me leave this only. I'll come back. Then, when I have 2 to 3, let us take one line here. Can I connect this way? I extend this, also I delete. Time being, I just take, I connect this way. This I will enter the elemental data over here. This is Y23. Then I have at the entrance of this, I have half line charging admittance. At this side also I have half line charging admittance. Then I have 3 to 4 connections. This also I complete. Between 3 and 4, I have a line Y34, and there is an half line charging element here. Here. Now I start naming them. We look at that at 2 lines. Here I have 3 lines. Here I have 3 lines. Here I have only 2 lines. Now I have to write 2. Here I have Y12, 1012, 1013, 30. You can just do that. 30 with respect to 3. This one is 4 with 4 with 2. This I will give as Y2012 or 21. Then this is Y23, like this, Y2023. Can I write this way? 21. When I have 2 to 1 connection, let me make it very clear. Y20, 2 to 3, Y224 due to 20. 2024, 2023, 2021. I completed bus 2. Now I look into this. Bus 3. 3 to 1, I have a connection, Y31. So I will rearrange this as Y30, 31. 3 to ground because of 3 to 1 connection. 3031. Now here 3 to 2 connection and Y23 this one. This I will write as Y3032. And this one Y3034. This is Y404. And this is Y4042. Now look into this. Entire problem which I was discussing, I just take it out. I rearrange to you for your perfect view. Okay. So this was bus 3, bus 1, this was Y13 like this. Now if I represent by pi model, each line will become pi, a straight admittance, a parallel to the ground. Straight admittance, parallel to the ground. Can you see here? Every element is represented as a pi model. Then work looks little exhaustive, but It is not going to be that exhaustive. Only the diagonal element gets modified. Rest of the elements of diagonal do remain the same what we did in the yesterday's discussion. So if you check y12, y12, 1 0 1 2 one side, and you check 1 3, y13 you have here, and y10 due to 1 2 3 you have element here. Now come to the bus number 2. At bus number 2 you have y221, same as y12 you have here y221, and you have a ground element 2021 due to this line. And if I check 2 to 3, I have here y23, a straight element. Because of this, there is an element to the ground, but 2 to ground, y20 due to 2 to 3 connection. This is called pi representation half line charging admittance. Similarly for 2 to 4, y2 to 4, an element, y24, and because of this, 2 to ground, y20 due to 2 to 4 connection. Similarly, I have bus number 3 to 1 connection, y30, 31. You can see here, y31, y30 due to 31 connection. And here, 3 to 2 connection, y23 or 32, due to which at this bus we have y30 because of connection 322. y3032. Then similarly for 30 due to 3 to 4. So why I did this? Yesterday it was a very straight problem. You were able to do by simple inspection. By visual you would have written it. But it need not be the case. The representation of the elements shall be pi model. And you cannot expect the entire transmission section be pi. 1 or 2 elements may be pi, rest may be lumped model. Then according to that representation, whichever is represented as a pi model, according to that connection, but 1 is pi, 1 to 2 is having a pi model, 1 and 2 get affected. 1 and 7 is having a pi model, 1 and 7 get affected. 9 and 10 is having a bus connection with the elemental data pi, account them. Rest remaining without pi, normal. So therefore this attention you need to keep in mind. So therefore, I wanted to just give you a view, if at all a representation go by pi model, how we should do. Okay? Then usually pi model is referred when you have transmission reduction into Y bus. Next, if like Y11 which I did, if anybody would like to know how is Y22, I can write it here. So Y22 at bus number 2, how do I write it now? 221, Y21, 223, Y23, 224, Y24. It was earlier like yesterday, as usual. Plus, the extra element is due to this, there is a Y2021. This is extra. Y20, comma 21 plus Y2023. 23 plus Y2420 means Y20 due to 24. This is your Y22 exhaustive length of Y bus diagonal element. So you can see these are new things. New. These were not there in the yesterday discussion. They have come now when I model in pi structure. Similarly, it will not change. Y23 is minus Y23. Y24 is minus Y24. Y2 is already done. 1, 2 is same as 2, 1 already being done. I need not represent it. Similarly, if I want to go for Y33. Y33 means I am at bus 3. Look at this. How many elements are there? 3 to 1, 3 to 2, 3 to 4. Straight. As well, 5 models admittances to the ground. 3031, 3032, 3034. You will have 6 terms in the representation. So you will have Y31 plus Y32 plus Y34 as usual. Plus I will have Y3031 plus Y3032 plus Y3034. Let me write it shorter here. then only you can see it. Plus y34 plus y30 31 plus y30 34, like this. So you will find these three as new, which were not there. Rest of diagonal remain the same. Off diagonals y34 is minus 34. Remaining are either we did not do it. Then at bus 4, at 4, you would see here, you have only two lines, one towards 2, one towards 3. I have to have y42, y43. That's all. So it will be y42 plus y43 plus y40 due to 42 plus y40 due to 43. One is here, one is here. That's the end. Then already you are done. 4-3 already done. 4-2 already done. 4-1 already done in the first one. Your work is complete. So this now a small change to the inspection method if transmission line models are with respect to pi model you need to accommodate. You will see it when I go for numerical problems. Once again after the completion of the portion, we will go with the numerical. This is to give you overview. You shall not think this is a new problem I am finding. It is something different. No, it's absolutely the same kind of problem. If the view is different. When I view with a lumped model, it becomes very simple problem. When I view with a transmission line model like a medium representation, a small extension of the work is visualized. Okay, this is what I wanted to convey as a change required. Then we will go with another representation, which is called as, can we do representation of admittance by Y bus by singular transformation method? How to obtain Y bus of a given system using singular transformation method? What is that singular transformation method? What it requires? What prerequisites we need to apply to get to Y bus of a system by singular transformation method of a particular interconnection? It means we are going to transform parameters and variables using the method singularity of the impedance matrix. What is that impedance matrix? What is that topology, graph theory required for that we have to get into. Before that, let us take one more approach. A elemental data which I have represented here, y12. How do I represent it? It is called as primitive element. What is primitive element? How primitive element is represented in the form of impedance, in the form of admittance? How a primitive element is generalized as an observation? And how that primitive element knowledge is used to obtain Y bus by singular transformation method is to be discussed in steps. To go ahead with, I just take up the concept of primitive element, primitive network. Then we'll go with the incidence matrices of the requirement. Okay. So this is extension of the yesterday's discussion is clear to you all. Okay. I go ahead with what is primitive element, how primitive element is represented in admittance form, impedance form, etc. But your syllabus highlights primitive element in admittance only. Impedance is not there. We will not put that much of effort on that. We will know how is that impedance and admittance connected to. Okay. So I just take primitive. Let me write general primitive element. Then it will be very clear. General primitive element. Let me take a simple representation how a element is represented. Okay, let me put over here. If I consider an element like this, Let me put it diagrammatically and let us discuss this. This I am referring from textbook Tag and L. Abhiyar, one of your text in the line which is given to you, and presently text is Power System Analysis, Modern Power System Analysis by Kothari, and followed by that original text which is Tag and L. Abhiyar. So from that reference I have taken this representation. No matter which of the book you refer, but concept must be clearly witnessed to you. Okay, I just take the representation how it is being done. Okay, then I represent this as VSK, some terminology, JSK, and this is YK or ZK. I'll highlight it. When is ZK, when is IK, like this is, I call this as bus Q, I call this as bus P, and I call this as current IK, and I call this as bus voltage, elemental voltage of this bus between P and Q as VK. Let me highlight them. VK is voltage across this branch, and VSK is the independent voltage source in kth branch. Okay, then I will write JSK, independent current source across kth branch. Let me write it and I'll turn back if you can note it down. JSK. Then I have one more elemental data. It may be YK or ZK. I said primitive admittance or impedance. Okay. It means I'm just trying to mention, I give you an outline. What is exactly this I have done? Let us take a power system layout, some interconnection like this. I have an element like this, bus 1, bus 2, and I may have elements like this, I may have elements like this, I may have a transmission between like this and future. I don't know. 2, this may be 3, this may be 4, and I may have an element going like this, 5, like this. Anything like this, a system. I don't know what next it is. My focus is general primitive element. What do you mean by general primitive element? A transmission line is connected by a conducting material. We all very clearly know. It do possess resistance, it do possess reactance. Because we are using DC transmission, AC transmission, it must possess reactance for that. Inductance part of the winding. Hello, please. I am able to listen to you, please.
Sir, all the sentences are looking blurred, sir. We can't see properly.
Okay, I just try to make someone to adjust the screen. Too much blur or you are at least able to? Just
no, sir, it is looking blurred, sir.
Okay, I'll try because
can't read sentence.
In the class I have to look both. I'll just try to zoom it and I'll try. Okay, let me try one. Now can you see anything blur or little magnified? What you find now?
No, sir, blur only.
I'll do it opposite. Okay. Now, any magnification has come? A little?
A little bit, sir.
I'll try in the same direction, okay? Because I'm moving the camera in some direction. I shall follow. Okay, I'm moving opposite. I think now it must be little clear.
Okay, sir.
Because if I move, I'll try. If I move another, I think it will blur again. I'll try and show you. 1 minute. Can you see? Some blur has come, I think.
Yes, sir.
I'll go back and with the best point of this I'll go. I think this is blur again.
Yes, sir.
I'll move. I'll make complete. No, it's not possible. Is it looking now at least?
Yes, sir. Yes, sir. It is looking.
No, it's working now?
Okay, sir. Let it.
Okay, fine. Okay. Because yesterday we have adjusted the camera and board distance and we have not zoomed it. Unless we interact with you, we could not. Now I think it is a little bit acceptable. Okay. And what I was interacting with you was when I have a transmission mechanism connected, the element between bus 1 and 2, 1 and 4, etc. Anything. I am focusing on this element. How this element is represented. What do you mean by this? So I would like to call it as general primitive element. When I was discussing very just in the moment, any element between bus 1 and 2 is a conducting material, they possess resistance and reactance. Then the primitive element is unconnected state of representation. It is just an resistance and inductance, and resistance and reactance, if I call it particularly, in the unconnected state. When I have removed this connection, both ends, what it represents to me? It represents an resistance and inductance of it. This unconnected state of electrical primitive element, basic element of representation of transmission line in unconnected state, what I measure, this we call as primitive element. When I have such several elements together in the system, primitive element now becomes primitive network. It would mean, when very simple statement of primitive means unconnected basic element of your transmission mechanism, like possessing a resistance and reactance. When it is unconnected, this element I call it as primitive element between 1 and 2. When I connect, it becomes elemental representation for you. It can be in impedance form, it can be in admittance form. No doubt I wrote R plus JXL, it must be impedance only. If I write it in this way, G plus JB, it becomes conductance and susceptance. It must be admittance at that time. This must be impedance. So, primitive element may be in impedance form or admittance form, which is unconnected, very native form of electrical parameter. This we call it electrical primitive element. Then, how this is visualized? Of course, in this section, which I represented as the simplest network, I have presented only resistance and inductance, or XL, if I consider only inductance. Now, it may not be the case. The element between 1 and 2 may have voltage source in the series, current source across this, anything may be there. That's called general primitive element. Any element between bus 1 and 2, bus 1 and 4, 4 and 5, any element which I am focusing can have like this between P and Q. 1 and 2 refers to P and Q in arbitrary representation. Between any two buses, P and Q, I may have a connection. The unconnected form of that representation I call as primitive element. Primitive element need not be only resistance, inductance or conductance and susceptance. It may be having, apart from that, a voltage source in the series, current source across that element. Then between those buses, this can be the generalized electrical form of primitive element. It need not be there in every position. In every position of element which I consider, this need not be there. There may be only voltage source and impedance or admittance. There may be only current source and voltage source need not be there. Invariably, electrically, the possibilities are an element between any two buses connected shall have voltage source, current source, and elemental data either in impedance form or admittance form. So this we call as general primitive element. So now I will come back. When I have any element between 1 and 2 or 2 and 3, 2, 4, etc. shall be visualized as the possible fullest length of which may be having along with the impedance or admittance like this yk or zk. I consider specially when I consider admittance, I delete this. When I consider impedance, I delete this. It means either it is an impedance or an admittance, it may possess a series voltage source which is independent voltage source in series with the admittance value or impedance value, or it may have a current source across the particular element which is connected, where this element is one of the physical elements between bus P and Q arbitrarily. It can be 1, 2 and 7, 2 and 9, etc. I am trying to describe this as general primitive element. Then I wrote it. Let this P and Q, between P and Q, I call this as branch number K. Branch may be 1, 2, 3, 4, K, M, N. N branches. 1000 branches in a system if you consider. 1, 2, 3, 4. If I increment in the computer, I equal to 1, 2, 3, 4, K, M, N. Like that, it keeps incrementing. In that regard, let us call a branch between bus P and Q as kth branch. Then I have all terminology falling as a K. Then what is that? Vk be the voltage across branch K. You can see here between P and Q, I call this as kth branch. Vk is called voltage across the kth branch. Then Vsk is the independent voltage source in the kth branch. Then I have JSK. JSK is the independent current source across the kth branch. Then I have IK, current entering the branch K. This I did not write here. IK. Then using this general term, I can specify my view. If I view this general representation only from admittance perspective, I will delete this. Then I call this as admittance view of primitive element. I call this as admittance view of primitive element. If I view it by ZK, then I call this as impedance view of general primitive element or impedance view of primitive element. No matter, we are working upon admittance bus. Why bus of our particular problem or understanding? I will fall into YK only. Means this element which I consider like this element is admittance. It is not only admittance, it is having series voltage source, parallel current source, and the voltage of that branch is Vk, etc. This can be the general terminology. If it is so, how to reduce this? This is general. There are so many things. Can it be really in every item which I have here? Absolutely no. It becomes a very complex connection to resolve it into. Therefore, this needs to be simplified into an admittance view. Admittance view. How to do it? My next step is, once I have a general primitive element described with the terminology, I will try to reduce this by admittance approach. When I consider this entire observation into admittance, how terminologies get modified, I have to account. That's called as admittance form of general primitive element. I just extend the word, and that will be our standing point for further discussion of our Y bus by singular transformation method. So I write here as admittance form of primitive network element. Then I call this as figure number 1. Just for easiness, I call this as figure number 1. Then I take the admittance view of which as the representation. figure 2. This can be simplified as this way. Leave to my observation. I'm going to transform this. I'm going to transform this as a generalized representation as P and Q. Then I have IK, then I have current, then I have YK, then JK, then I have VK between these two. Can you see here? This network which is general, now it is observed as admittance form only. Then I have this as figure 2 for our observation. This is called as representing this into admittance form. When I represent it into admittance form, you might come across what is JK, Newton. There was no JK here. JSK was there. It was independent current source. VSK was independent voltage source. VK was a voltage across the branch. Then it got resolved into VK as usual, and VSK has gone. JSK has gone. Then how to represent it? Let me represent the circle. It will be easy for you. Like this. Current source. JK. Now I just write VK is the voltage across kth branch. Then IK is the current through kth branch. Then I have JK. Can you see here? JK is equivalent. Let me write here. Equivalent current source in, let me write across kth branch. You might find how you get this. You have to have transformation. When I mathematically reduce it, I will have some term represented as JK. You will see it, no problem. So this is how this network is viewed in this way for admittance form of observation. Once it is being done, observe a change. You got VSK disappeared. You got JSK disappeared and getting transformed as JK. And VK remaining VK, IK remaining IK. Current through kth branch. Now my work is to show you what's the outcome of this. The outcome of this is, if you look into this figure number 2, if I apply KCL for this, IK, JK, IK, JK must be equal to YK into VK. If I apply KCL at this junction, at the peak bus, incoming current must be current going out. Current going out is admittance into voltage. So I have to do it. Before doing it, come to this network. Apply similar concept over here. KVL. Apply KVL for this. Keep the equation simplified. And remedial things, if you refer over here, you can compare these two. I would otherwise say, this general primitive element, when I make element as admittance, if I reduce this to this network, figure 1 and figure 2 must be equivalent to each other. When they are equivalent to each other, I can compare elements with the other. That I have to do. Then this is my final observation of general primitive element with the admittance goggle. That's all. Now let us write the observation. With respect to figure number 1 and figure number 2, what I can write? So I shall wipe it out. Hope this is taken. This portion I will eliminate, which is independent voltage source. Look at the terminology, minus and plus, and it's a current source, and admittance is retained here. This portion I will take it out. A short 3 to 4 lines of relationship I will justify here. Okay. From figure 1 and 2, I can write from figure 1 and figure 2. When I make equivalent of them, I have here IK plus JSK is equal to VK plus VSK into YK. You observe it, what is being done? In the first figure, we had a JSK current entering to the P, IK entering to the P. IK plus JSK is the net current entering the path. That's called IK plus JSK is equal to the current going along the path is voltage across the branch was VK. Independent voltage source in the series path was VSK. Then net voltage of the PQ stand as VSK plus SK. VK plus VSK into admittance of the path. If I take a product, this represents me current. So sum of the incoming current is equal to sum of the current going out. Like a KCL, it's called as a power invariance. Incoming power must be dispensed to the network. Like that, IK plus JSK entering has to be dispensed other side, which is being dispensed as VK plus VSK into YK. Now I will simplify this. This will be equal to VK YK plus VSK YK. Then what I will do, I will transfer this JSK other side. Therefore, IK equal to VSK YK minus JSK. You can look here what I did, plus VK YK. This I will take other side as minus JK plus VK YK equal to IK. This I will take other side. Therefore, IK plus JK equal to VK YK. What is this? Where JK is the equivalent current. Equivalent current which is due to VSK YK minus JSK is represented over here. It is taken other side. Now you compare this with this block, which is IK entering here, JK coming over here. IK plus JK is the current leaving here. What is the current leaving here? VK into YK, which I got. It means to say figure number 1 and figure number 2 are equivalent to each other. But you see the simplicity is the current entering, current equivalent current source of the branch, and VK, YK are the representation. Suppose in general, this is K branch only. It becomes I bar plus J bar plus equal to V bar, and this becomes a matrix called Y matrix. This becomes primitive elemental admittance matrix. This becomes primitive matrix. When I have only one K branch, YK only. This is only one K branch. Between P and K, only one branch, YK. Like that, I have hundreds of elements in the power system. Then I will call this as a vector of current. IK becomes vector of I. JK becomes vector of J. VK becomes vector of branch voltages. And YK, single element data becomes number of elements together become a matrix. This is an outcome of observation of primitive elements in admittance view. So therefore, I will stop over here. So vector of I, injected current, vector of equivalent current, and vector of branch voltages multiplied with the primitive matrix give you the equivalent. So therefore, figure 2 is valid with this derivation. This is called as obtaining primitive form of elemental data in admittance form. This is one short derivation we would need to remember. And further, I will take you from this matrix. What is the observation of Y. How Y matrix look like? What are the properties of Y matrix? How many elements will be there? Where all elements are placed? Then we will take this to further interaction as singular transformation method. Okay. So I'll stop here and we'll go with the further discussion in the next class.